Microscopic technique. The microscope is an instrument that is used to visualize objects that are too small to be visualized by the human eye. The science and technology that resolved around the use of microscope to see such microscope object is termed as microscope. The science of microscope is essential to biology, as a vast majority of biological science and its component is microscopic in size. The development of microscope is thus intertwined with the development of understanding the cellular component of life. The initial development of a modern day microscope has been attributed to Dutch spectacles makers, while significant improvement was done by Antony van Leeuwenhoek in 1670, who was able to magnify an object up to 300 times. The microscope have since then discovered has been developed much and presently there is a wide variations of type available to the biologist. The microscope can be classified based on the source of illumination of object under the observation. 1. Optical microscope, often refers to as a light microscope, use a visible light as a source and the symptoms of lenses that generates a magnified images of an object. 2. The fluorescent microscope involves the visualization of a fluorescence tagged cellular components that observes light at one frequency and then later emits light at a different frequency. 3. The electron microscope uses a beam of electron that strikes the object to be imaged, and the reflected or scattered electron is directed to generate a three-dimensional image. Visualization of cell and subcellular component by light microscopy. The entire branch of cell biology and molecular biology is greatly dependent on microscope for visualization of histological structures, cell interaction, cellular structure and function, subcellular structures, protein interactions, etc. An appreciation of microscopic tools available for biological investigation is critical to understand the present status and future direction of the research. The proposal of the cell theory by Matthias Sheldon and Theodore Schwann in 1838 was directly influenced by microscopic observation of plants and animal tissue. The recognition of a cell as the fundamental unit of all living organisms is thus based on the observation made with the light microscope. Light microscope. The light microscope is a basic tool for cellular visualization. The recent technical improvement have increased the ability to document greater detail of subcellular structures. The contemporary light microscope can modify object up to about 1,000 times. Since most cells are between 1 to 100 micrometer in diameter, they are observable by light microscope. The larger subcellular organelles, that is nuclei, chloroplast and mitochondria, can also be visualized using the light microscope. The light microscope, however, cannot sufficiently reveal fine detail of cell structures. 1. Resolution. The resolution is the ability of microscope to distinguish between the point separation by small distance. Resolution is the ability of microscope to distinguish between the point separation by small distance. The resolution is more important than magnification, as this increases the detail present in a microscopic view. The image can be magnified as much as desired, for example by projecting on a large screen. However, that does not increases the observed detail. 2. The limit resolution of a light microscope is approximately 0.2 micrometer. The two objects is separated by the lens, that is distance appears as a single image rather than being distinguished as separate. 3. The resolution of light microscope is determined by two factors: the wavelength lambda of the visible light and the numerical aperture Na of the microscope lens, which is its light gathering power. The resolution power is equal to 0.61 lambda by Na. The wavelength of the visible light is 0.4 to 0.7 micrometer. So the value of lambda is fixed at approximately 0.5 micrometer for light microscope. 4. The numerical aperture can be described as the size of the cone of light that enters the microscope lens after passing through the specimen. It is determined as Na is equal to n into sin into alpha, where n is the refractive index of the medium through which the light travels between the specimen and the lens. The value of n for air is 1.0. 5. The value of n can be increased by the maximum of approximately 1.4 by using an oil immersion lens to view the specimen through a drop of oil. 6. The angle alpha corresponds to the half of the width of cone of light collected by the lens. The maximum value of alpha being 90 degree. The sin alpha is equal to 1. Therefore, the highest value of NA is 1.4 while using an oil immersion lens. 7. The theoretical limit of resolution of light microscope can therefore be calculated as follows. Resolution is equal to 0.61 into 0.5 divided by 1.4 is equal to 0.22 micrometer. The basic principle of light microscope is shown in the figure. An image of object specimen is formed by the objective lens, which typically provide magnification the range of 10x to 100x. This magnified image is then viewed through the eyepiece ocular, whose magnification is usually 10x. 8. The total magnification of microscope is obtained by multiplying the objective and eyepiece magnification. Typically, the total magnification are in the range 100x to 1000x. The image is usually not presented as a real image, but rather as a virtual image viewed through the eyepiece. The definition for the microscope magnification is the following. The magnification is equal to angle sustained by a small object as seen through the microscope divided by the angle when the same object is viewed by the naked eye at a distance of 250 millimeter. Using the denomination in the figure, we can express the magnification of the object m0 and eyepiece mc as m0 is equal to h divided by capital H divided by small h is equal to b by a, and me is equal to 250 bar fc. 9. If the image formation if in image formation, one important aspect is the focal length, that is which is the distance between the lens and the image formed. The focal length is a measure of magnification. In modern microscope, the objective is designed for a optical tube length, so including both the focal length and magnification on the barrel becomes somewhat redundant. Several types of light microscope are routinely used to investigate different aspects of cell morphology. One such variation is a bright field microscope, in which the light directly passes through the cell, and a differential observation of visible light by different components of the cell gives the observer the ability to distinguish the different components of the cell under observation. Often cells are stained with dye that reacts or binds to protein or nucleic acid, which enhances the contrast between different components. Prior to staining, the cell and their internal structure are often prevented from breaking down by using fixatives such as formaldehyde, or by using the preservatives like ethyl alcohol. The basic difference is that while fixative essentially kills the cell by disrupting bond formation and altering protein structures, preservatives just renders the cell inactivities, often be dehydration as in case of ethyl alcohol. Apart from for staining, the optical variation in light microscope components can also improve the contrast between the different cellular components. Phase contrast microscope. The phase contrast microscope is an optical microscope technique that converts the phase shift in light passes through a transparent specimen to brightness changes in the image. The phase shift themselves are invisible but becomes visible when shown as brightness variations. 2. Differential interference contrast microscope. The differential interference contrast DIC microscope is an optical microscope technique used to enhance the contrast in unstained transparent samples. The differential interference contrast microscope works on the principle of interferometry to gain information about the optical path length of the sample to see otherwise invisible feature. The differential interference contrast microscope works by separating a polarized light source into two orthogonal polarized mutually coherent parts, which are spatial displaced, sheared at the sample plane and combined before observation. The interference of the two part at the combination is a sensitivity to their optical path difference, that is the product of refractive index and the geometric path length. The application of light microscope has been improved by additional use of video camera and computer imaging and enhanced processing of generated images by software analysis. In recent time, video enhances the DIC. In recent times, the video enhanced direct interference contrast microscope has allowed the visualization of cell organelles movement without preservation or fixation. However, these enhancements do not increases the theoretical limits of resolution. The main difference between the stain and dye in histology is that the stain is a mixture of several dye, whereas the dye is a substance that highlights intracellular and extracellular elements of the tissue. In addition, a stain gives contrast to the tissue as it highlights different components with different colors. On the other hand, a dye may highlight only a specific components within the tissue. Microscopy of living cells. Fluorescent microscopy. The intracellular distribution of molecules is widely observed by the application through the very sensitive method of fluorescence microscopy. In this method, a fluorescent dye is used for labeling molecules of interest within the fixed or living cells. The fluorescent dye is a molecule that absorbs light at one wavelength and emits light at a second wavelength. This fluorescence is detected by the illuminating the specimen with a certain wavelength, which excites the dye by elevating the proton within to an elevated state. The proton then loses the energy in the form of photon in a different wavelength. This is an all or nothing event. To observe the photon must contain a quality of energy, a quantum that exactly matches the energy of electronic transition. A molecule that has observed a photon is in a excited state, which is generally unstable. An electron lifted into a higher energy orbital usually returns rapidly to its normal lower energy orbital. The excited molecules decay to be stable ground state, giving up the absorbed quantity as light or heat or using it to do chemical works. The light emission accompanying decay of excited molecules called fluorescence is always at a lower wavelength, lower energy than that of observed light. One of the most commonly used fluorescent tag is derived from the green fluorescent protein GFP of jellyfish Acura victoria. When excited by absorption of a photon of light, the green fluorescent protein emits light in a green region of the spectrum. The green fluorescent protein has 11 standard barrel structures and light absorbing emitting center of protein comprises tripeptide serine 65, TYR 66 and glycine 67. 2. The variant of this protein with different fluorescent spectra can be produced by genetic engineering of the green fluorescent protein gene. A yellow fluorescent protein YFP is produced by replacing the alanine 206 in green fluorescent protein by lysine residue, changing the wavelength of light observed and fluorescence. Other variant of green fluorescent protein fluorescence blow BFP or cyan CFP light and related protein MRFP1 fluoresces red light. The fluorescence recovery after photo bleaching FRAP. The rate of fluorescence recovery after photo bleaching FRAP is a measure of rate of lateral diffusion of fluorescence tagged lipid. Using the fluorescence recovery after photo bleaching, the technique movement of the lipid and proteins on the cell membrane can be observed and the rate of their movement measured. 1. The lipid in outer leaflet of plasma medium are labeled by reaction with the membrane impairment fluorescent probe red, so the surface is uniformly labeled when viewed with the fluorescent microscope. 2. After a small area is bleached by irradiation with an intense laser beam, leaving that area non-fluorescent. 3. With the passage of time, labeled lipid molecules diffuses into the bleaching region and it again becomes fluorescent. Fourth, from the time course of fluorescence return to its area, the diffusion coefficient for the labeled lipid is determined. 5. The rate are found to be typically high. A lipid moving at this speed could circumvent an E. coli cell in 1 second. Fluorescent resonant energy transfer, or FRET. The fluorescent resonant energy transfer (FRET) is a method to identify the protein-protein interaction within the cell. 1. In this method, the energy of excited molecules, the donor passes directly to a nearby molecules, the acceptor, without emission of photon exciting the acceptor. 2. The acceptor then returns to its ground state by emitting photon having a longer wavelength than the original exciting light and the fluorescence emission of the donor. This second mode of decay (FRET) is possible only when the donor and acceptor are close to each other within 1 to 50 Armstrong. 3. Thus, very small change in the distance between the donor and the acceptor register as very large changes in fluorescent resonant energy transfer, measured as the fluorescence of acceptor molecules when the donor is excited. With sufficiently sensitive light detectors, this fluorescent signal can be located to specific region of single living cells. 4. The fluorescence resonance energy transfer has been used to measure the CAMP concentration in the living cells. The gene for GFP is fused with that for regulatory subunit of CAMP dependent protein kinase, and the gene for BFP is fused with that for catalytic subunit. When these two hybrid proteins are expressed in cell, the BFP donor excited at 380 nanometer, emission at 460 nanometer, and GFP acceptor excited at 475 nanometer, emission at 545 nanometer in the inactive protein kinase A are close enough to undergo fluorescent resonance energy transfer. The images generated by the standard fluorescent microscope are often blurred due to out-of-focus fluorescence. This can be improved by using a computational approach called image convolution, which uses generated image taken from different depth to produce a sharper images. Confocal microscope. The confocal microscope allows the image to increase contrast and detail by analyzing the fluorescence from only single point in the specimen. 1. A small point of light supplied by the laser is focused on the specimen at depth. 2. The fluorescence emitted is then passed through a pinhole or confocal aperture placed at precisely the point where light emitted from the chosen depth of specimen comes to focus. 3. The light is then collected in a detector, that is a video camera, or therefore only light emitted from the plane of focus can reach the detector. 4. The scanning across the specimen generates a two-dimensional image of the plane of focus, which is much more sharper image than standard fluorescence. Multiphoton excitation microscope. The multiphoton excitation microscope is an alternative approach to confocal microscope in the case of living cells. Here, the specimen is illuminated with the wavelength of light, such as that excitation of fluorescent dye, which requires the simultaneous absorption of two or more photons. The probability of two photons simultaneously exciting the fluorescence dye beam is focused. So, fluorescence is only emitted from the plane of focus of the input light. The localized excitation automatically provides three-dimensional rotation without passing it through a pinhole aperture. This procedure does minimum damage to living cell, thus allowing three-dimensional imaging. Electron microscopy (EM). The electron microscopy is a much more powerful microscopy technique that can analyze the detail of cell structure and does not use any forms of light energy to aid in visualization. The technology was developed in 1930s and was first applied to observe the biological specimen by Albert Claudy. Kelt Porter and George Pallady in 1940s and 1950s. Due to the shorter wavelength of electron as compared to light, the electron microscope can achieve as much greater resolution. The wavelength of electron in an electron microscope can be as shorter as 0.004 nanometer. This sets the resolution to be 0.002 nanometer. However, in practice, this value is not achievable as numerical aperture is a limiting factor in electron microscope, which limits the resolution to 0.2 nanometer. The two types of electron microscope are widely used to study cells. A transition electron microscope. The specimen are fixed and stained with heavy metals salts, which provide contrast by scattering electrons. The specimens are fixed and stained with heavy metal salts, which provide contrast by scattering electrons. A beam of electron is then passed through the specimen and focused to form an image on fluorescent screen. The electrons that encounters a heavy metal ions as they passes through the sample are deflected and do not contribute to the final image. So stained, so so the stained area of the specimen appears dark. In contrast between the two adjacent area in a transmission electron microscope, the image can be defined as the difference in the electron density in the image plane. Due to the scattering of incident beam by the sample, the amplitude and phase of the electron wavelength changes, which results in the amplitude contrast and phase contrast. Most of the image have both contrast component. The specimen is most often an ultra thin section less than 100 nanometer thick or suspension on a grid. An image is formed from the interaction of electrons with the sample as the beam is transmitted to the specimen. The image is then magnified and focused onto a image device such as a fluorescent screen, a layer of photographic film, or a sensor such as a charge coupled device CCD. B. Scanning electron microscope SEM. In scanning electron microscope, the electron beam does not pass through the specimen. Instead, the surface of the cell is coated with heavy metal and the beam of electron is used to scan across the specimen. The electrons that are scattered or emitted from the sample surface are collected to generate a three-dimensional image as electron beam moves across the cell. However, comparatively the low resolution limit of about 10 nanometer, the scanning electron microscope is used to study whole cells rather than subcellular compartments. The electrons interact with the atoms in the sample, producing various signals that contains information about the surface topography and the composition of the sample. The electron beam is scanned in a raster scan pattern, and the position of the beam is combined with the detected signal to produce an image. The scanning electron microscope can achieve a resolution better than 1 nanometer. The specimen are observed in a high vacuum in conventional scanning electron microscope, or in low vacuum or wet condition in variable pressure or environmental scanning electron microscope, and at a wide range of cryogenic or elevated temperature with a specialized instrument. Staining of EM electron microscope. The specimen for electron microscope can be prepared by either positive or negative staining. 1. In positive staining, the tissue specimen can cut into thin sections and stained with heavy metal salts like osmium tetroxide, uranyl acetate, and lead citrate that reacts with lipid, proteins, and nucleic acid. The bound region of the cell appears darker in the final image. Alternatively, the positive staining procedure can also be used to identify the specific macromolecules within the cells. The three-dimensional view of structure with the resolution of 2 to 10 nanometer can also be generated using the tomography, which generates images by computer analysis to multiple two-dimensional images over a range of viewing directions. 2. Negative staining. Negative staining is useful for visualization of intact biological structures such as a bacterial cell. In this method, the biological specimen is deposited on a supporting film and heavy metal stain is around its surface. The unstained specimen is then surrounded by a film of electron dense stain, which generates an image in which the specimen appears light against a stained dark background. 3. Metal shadowing. Metal shadowing is another technique used to visualize the surface of localized subcellular structures in transmission electron microscope. The specimen is coated with a thin layer of evaporated metal such as platinum. The metal is sprayed on to the specimen from an angle so that the surface of the specimen that faces the source of evaporated metal. This causes a differential shadow effect, giving the specimen a three-dimensional appearance. Freeze fracture. The sample preparation for studying the membrane structure through transmission electron microscope often requires the process of a freeze fracture in combination with the metal shadowing to allow visualization. The 4 key steps in making a freeze fracture replica are: 1. Rapid freezing. 2. Fracturing. 3. Replication. 4. Replica cleaning. In routine protocol, a pre-treatment step is carried out before freezing, typically comprising fixing in glutaraldehyde followed by cryoprotection in with glycerol. For this process, the specimen are frozen in liquid nitrogen at minus 96 degrees centigrade and it is fractured using a knife blade. This process frequently splits the lipid bilayer, which reveals the interior face of a cell membrane. The specimen is then shadowed with platinum and biological materials dissolved in acid, producing a metallic replica of the surface of the sample. Examination of such a replica in the ultraviolet microscope reveals many surface protein that spans the lipid bilayer. Freeze etching. The freeze etching is the sublimation of the surface ice under the vacuum to reveal details of fracture phase that was originally hidden. To reveal details of fracture surface, the ice must be removed. This needs to be done by sublimation of ice to preserve the surface structure of a specimen. The ice is directly transformed into the water vapor without going through the liquid state, which would lead to changes in volume and structural damage. The sublimation or condensation process of water depends on the saturation pressure at a temperature and the effective partial water pressure of water or ice in the chamber. Performing freezing etching until the sample is completely ice freeze is called freeze drying. This process only works for small samples to be performed in a reasonable time. It is done in several steps by heating up from around minus 20 degrees centigrade to minus 60 degrees centigrade, maintaining the temperature of each step for a certain time. This can take up to days. Resolving power of different microscope. Resolution is the ability of microscope to distinguish between the point separation by small distance. The limit resolution of light microscope is approximately 0.2 micrometer. The two objects separated by less than this distance appears as a single image rather than being distinguished as separate. The resolution of light microscope is determined by two factors: the wavelength of visible light and numerical aperture of the microscope lens, which is the light gathering power. Resolution is equal to 0.61 lambda by Na. Due to the shorter wavelength of electron as compared to the light, the electron microscope can achieve a much greater resolution. The wavelength of electron in an electron microscope can be short as 0.004 nanometer. This makes the theoretical limit of resolution to be 0.002 nanometer, but such a resolution cannot be achieved in practice because the resolution is determined not only by wavelength but also by numerical aperture of microscope lens. The numerical aperture is a limit factor for electron microscope because inherent property of electromagnetic lens limit their aperture. angles to about 0.5 degree, resulting in a numerical aperture of about 0.01. Thus, under optimal condition, resolving power of electron microscope is approximately 0.2 nanometer. However, in case of biological samples, the resolving power of is lower at 1 to 2 nanometer due to lack of contrast in biological samples. Image processing method in microscopy. The image produced by microscope can be converted into digital form for storage. Its analysis or processing an image prior to display and interpretation is called microscope image processing. The digitization process forms the digital image from the optical image which is obtained from microscope. As same as traditional image processing, the microscope application also used a fundamental technique to produce the information contained in the microscopic sample. Due to the distortion caused by the camera and eye holes and the limitation effect, one need to adjust the brightness contrast of the image. Also, the first step image averaging need to apply to reduce the noise and image correction. For 3D image analysis, one need to take a series of images at the fixed position but at a dissimilar local focal depth. Since the majority microscopic samples are essentially transparent and the depth of the field of the focused sample is exceptionally narrow, it is possible to capture images through the three-dimensional objects such as using 2D equipments like confocal microscope. Measurement of microscopic object. The microscope may be equipped with a scales called reticule that is built into one eyepiece. The reticule can be used to measure any planar dimension in a microscope field, since the ocular can be turned in any direction and the object of interest can be repositioned with a stage manipulator. 1. To measure the length of the object, note the number of ocular divisions spanned by the object, then multiply by conversion factor of the magnification used. 2. The conversion factor is different at each magnification. Therefore, when using the reticule for the first time, it is necessary to calibrate the scale by focusing on a second micrometer scale, a stage micrometer placed directly on the stage. 3. The usual scale consists of 50 to 100 divisions. Fine tuning of the focus of the eyepiece in order to make the scale as sharp as possible. Also adjust other eyepiece to match the focus. Any ocular scale must be calibrated using the device called stage micrometer. 4. The stage micrometer is simply a microscope slide with a scale etched on the surface as shown in the figure. A typical micrometer scale is 2 mm long and at least of it should be engraved with the division of 0.01 mm 10 micrometer. 5. Suppose that the stage micrometer scale has a division that is equal to 0.1 mm, which is 100 micrometer. Suppose that the scale is lined up with a ocular scale at 100x. It is observed that each micrometer division covers this same distance as 10 ocular division. That one ocular division smallest increment on the scale is equal to 100 micrometer at 100 power. The conversion to other magnification is accomplished by the factoring in the difference in magnification. In the illustration, the calibration would be 25 micrometer at 40x, 2.5 micrometer at 400x and 1 micrometer at 1000x.